Okay, so welcome everybody. You're watching the motivic geometry seminar. Today we have Ryomei Iwasa talking about Chern classes with modulus.
Thank you for the introduction and thank you for the invitation. It's my first online talk, so I'm a bit nervous. But okay, let's start. Today I'm going to talk about the Chern classes with modulus. So this is a joint paper with Wataru Kai. It's published at Nagoya Journal last year. So the paper is a bit technical, so let me try to explain what's going on there and what we wanted to do. So, so it's about Chern classes. So let me begin with the usual Chern classes. I mean the case without modulus. So in this case, it's quite easy to construct the Chern classes. So let me explain that. So let E be a cohomology theory on the category of schemes. So to make it precise, let's assume this is a functor from the category of smooth schemes over a fixed base S. So it's contravariant functor from this category to say vector. And we want to assume this is multiplicative. So let's assume this is Lax symmetric monoidal. So we don't need a full coherency, but let me assume this is the easiest way to write down. And we assume some axiom. This satisfies first Zariski descent. I mean, this is a sieve with respect to Zariski topology, and assume this has a push forward. With respect to regular cross immersion. And plus some usual compatibility. And finally, we want to assume this cohomology theory satisfies the projective Mantel formula. To be more precise, the last condition means so this is projective space, and because we have push forward with respect to regular cross immersion, we have push forward, and this is some hyperplane section. And we also take projection. Prove back with respect to projection, and then the projective bundle formula says this is equivalence. So this is our axiom, and I will explain how to construct the Chern classes for this cohomology theory. So in particular, we don't need homotopy invariance to construct Chern class. So example, our main example is motivic complex. So, like this. So if S is field, and then this is given by Bloch the cycle complex. block cycle complex. Because I will use this block, this complex later, so let me recall the definition briefly. This is a complex, and at degree n, this is free abelian group generated by B. This is a closed subscheme of X times delta n, integral closed. Here, delta n is as usual spec k is 0 Tn divided by sigma Ti minus 1. And the integral closed and meeting all faces properly. All faces properly. Then this abelian group forms simplicial abelian group, and this is the definition of blocked cycle complex. Okay, so let me now explain how to construct Chern class. So first definition. Oh, I shouldn't erase this. So first Chern class. So suppose we have a line bundle on X, on our scheme X. Then the definition of first Chern class is, so this is line bundle, we take zero section. So this is regular growth immersion, so we can take push forward of 1 and take pull back. So this is in E naught X, I mean just a pi naught of EX. So this is the definition of, I think this is the usual definition of first Chern class. Then we can construct higher Chern class as follows. So let E be a vector bundle of rank R on X. And let's consider the associated projective space like this. And then we have a first Chern class of the dual of the canonical line bundle in here. And let me denote this by xi. Then let's consider the following map from X. First, take fullback with respect to this projection, and take multiplication with respect to i's power of xi. So this goes to PE, and take sum from I0 to R minus 1. Take sum. Then the projective bundle formula implies this is isomorphism. Therefore, it follows that there exists unique CI in E star E naught X such that it satisfies the usual C1 R minus 1 plus CR minus 1 psi plus R is 0 in here in right. So and this is called ice Chern class of E. And we can easily extend this construction to higher Chern classes. For this, we consider the BGLR, the classifying stack of vector bundle of rank R. And this is Zaleski locally represented by this simple shell scheme BGLR. And we consider the projective space associated to the universal vector bundle. Then we, as before, we can think about the first Chern class of this first Chern class of the canonical line bundle of this projective space. And again, we have projective bundle formula. So by the same formula, we get Ci in B naught BGLR. And this is, we can regard this is a map from BGLR to E. And we can show this is independent of R if R is bigger than I. So by taking plus construction and taking homotopy group, we get a map from K theory to this our cohomology theory, and for positive homotopy groups. So this is about usual Chern classes. So is there any question so far? Okay, then let me turn to the case with modulus. Then things become more complicated. So modulus. Let me first introduce some notation. So a modulus pair which appeared in Kai's talk last week. So modulus pair is a pair XD of a, let me say, smooth scheme X over S. So this is a modulus pair over S. S is a fixed scheme, and an effective Cartier divisor. And morphism of modulus pairs from XD to X prime D prime is the morphism of S schemes which induces a morphism of subschemes from D to D prime regarding D and D prime as closed subschemes of X and X prime. And this notion of morphism, this morphism is different from the one in Kai's talk last week. I don't want to recall the definition, but yeah, it's different. And this morphism is suitable for our purpose. Anyway, we get category. I denote this category by MSM over S. And we want to consider cohomology theory on this category. So it's like morphism as a functor from this category to spectra, and which satisfies similar property as we thought before. So Zariski descent, push forward with respect to regular cross immersion, and projective bundle formula. It's not precise, and but I don't want to make it precise here because it's not so important in my talk. Instead, let me just say these are the properties which come from the following example. Suppose we have some cohomology theory, good cohomology theory from the category of schemes to spectra, which satisfies this property. Then it's more clear what does it mean, right? And so then for modulus pair XD, we consider EXD to be the homotopy fiber from EX to ED. Then this gives a functor from this our category to spectra, and which satisfy these properties. Because though I haven't defined it, these are the property which come from this example. So this, we can say this is a cohomology theory with modulus. Okay, and this example also says if we have a reasonable cohomology theory on the category of schemes, then we get a cohomology theory with modulus. So why we need to think these modulus things? So the reason is simple. So this is just because EXD sometimes is easier to construct. So to be easier to construct, to define or describe, and ED is the singular. So let me give an example. So this is our main example, and the cycle complex with modulus defined by Shuji Saito and Federico Vinga. Which generalize the previous notion additive higher Chow groups introduced by Brock and Eno. So to define it, let XD be a modulus pair. The cycle complex with modulus is written like this. The subcomplex of Brock's higher Brock's cycle complex, which I recalled at the beginning, the subcomplex. subcomplex generated by or spanned by the integral closed subscheme of x times delta n, which satisfies, of course, the phase condition. This is the condition here, and moreover, we assume this satisfies the modulus, so-called modulus condition. So this is a condition about the boundary, I mean along D, and which is defined as follow. So let V bar be the closure of x times delta n bar closure, where x n bar is a compactification natural compactification of delta n and non-canonically isomorphic to Pn. So this is the closure, and we want to consider the blow up of x times delta bar n at d times delta bar n, sorry, d times delta bar n intersect x times delta bar n minus delta n with reduced structure here. Yes, let's consider this blow up. Then the modulus condition says, the strict transform of V bar does not meet the strict transform of B times delta bar n. So this is the definition. So the simplest case which satisfies the modulus condition is if this closure does not meet d times delta bar n, then of course it satisfies the modulus condition. But we allow some more, how can I say, more closed subscheme which defined here. Okay, so this is the definition of a cycle complex with modulus. Then this assignment xd to d star xd satisfies. This is a cycle, so it's easy to see. This has proper push forward, and also projective bundle formula is not difficult to show. And this is factorial, sorry, contravariant factorial for flat morphisms, flat maps. This is okay, but may not be factorial as usual. Cycle complex may not be factorial for arbitrary morphism.
Sorry, can I have a question, a quick question?
Of course, yes, please.
Which descent, the strongest descent does this construction satisfy?
No, it does not.
No, no descent.
Yeah, so I'm going to talk about it. So yeah.
Okay, sorry.
No, it's okay. Thank you for the question. So this satisfies proper push for the projective bundle formula, and it's contravariant factorial for flat morphisms, but may not be factorial for arbitrary morphisms maps. And and this does not satisfy. There's a current example does not satisfy even the risky descent. So we need to localize this complex at least, and the theorem of Kai Wataru says, okay, if we Nisnevich sheafify of this cycle complex, by this I mean the press sheaf given by, sorry, press sheaf over u x extends u times xd like this. Because this is a contravariant factorial for flat morphisms, this gives a press sheaf on the category of on small side of x, and take Nisnevich sheafification of this cycle complex, then yields a functor from all category to, oh sorry, let's assume S basis field. Then after Nisnevich sheafification, this yields a functor from this category to spectrum. Okay. Is there any question?
I have one question. Is there a
Yep.
example showing that this is not a Nisnevich sheaf? That it
What's
doesn't
the counter example?
Yes.
Something global, let me see. Global, but not projective space. Maybe I can't immediately. I can't answer immediately. But
Okay. Thanks. No problem. Thanks.
Sorry. Maybe someone in the audience knows. Please write the answer in the chat if you know the answer. Okay. Anyway, sorry about that. And okay, now the question is, can we construct Chern class for cohomology theory with modulus? But this is not clear in the by the following reason. So let's consider the vector bundle of rank R on X, and okay, let X be a modulus pair. And then with trivialization along D. So then this pair is an element of the relative K group. So it's natural to ask if we can construct the Chern class for this pair vector bundles with trivialization. However, okay, yes.
There's a question in the chat. I think there might be a typo on the blackboard.
Oh, typo. Does
The
not.
question is if it does or does not satisfy heuristic.
Oh, okay. Yes. Thank you. That's not.
Right. Yeah,
thank you. Yes. Thank you. And okay, so this pair gives an element of relative K group. So it's natural to ask if we can construct a Chern class of this pair. Okay, then we have a projective bundle formula, almost by definition, by the requirement. meaning this is direct sum of exd. However, this xi first Chern class of O1, this is in EPE, so absolute cohomology theory, but this does not lift to our relative theory. We cannot expect it because O1D is not trivial, right? It's not trivial. Unless as a rank is 1. So we yes. So this is a problem. However, but our main idea is it may be possible to lift the R's power of this design to this relative cohomology theory. Then by the same formula, for usual Chern classes, we get a Chern class in this cohomology theory. And what we have done is we constructed this lift, a lift in this relative theory for cycle complex with modulus. So let me explain it more precisely. Any question? Oh, oops. Okay.
It's okay. I think it's fine.
Yeah.
Sorry, I have, this is a question from Vanya Panin.
Yes.
Very silly question. You always use the term cohomology,
Yes.
but you always write lower subscript.
Oh yeah, that's right.
So your E lower star, is it contravariant or covariant?
It's contravariant, but this is homotopy groups.
Yeah.
By lower star, I mean homotopy groups. But yes, you are right. Usually, we assume this is graded. I just said spectra, but we should have usually grade or tape twist. So,
but it is contravariant.
It's contravariant, yes.
Okay, thank you.
Functor is contravariant. So this is star means.
Yeah, this is grading.
Yes, yes.
Okay, thank you.
Thank you. So let me explain the construction. Okay. So what I want to construct. So let XD be a modulus pair over field K, and let E be a vector bundle of rank R on X with trivialization alpha, sorry, from E restricted to D to ODR. And we construct we construct the Chern class of this pair in cycle complex with modulus. Sorry, yes, cycle complex with modulus after Nisnevich simplification, and sorry, yeah, alpha in pi naught of this. Nisnevich simplification of the cycle, this cycle complex. Okay, let me explain the construction. So let's check Zariski covering. UI to X with alpha I. This is the trivialization of UI to O UI R. Zariski locally every vector bundle is trivial, and we can also assume this which extend our given trivialization alpha restricted UI. Let's take such Zariski coupling. And let's take a check nav of this coupling. So then this projective space, if we take base change to this simplicial scheme, co-simplicial scheme, yes, then this is just, so this is, wait, this is
Simplicial.
yes, thank you. This is simplicial scheme, so, and if we take base change, this is a simplicial scheme, and at each degree, this is just a trivial projective space. Because of the trivialization, we have such isomorphism. Okay, good. So next, let's consider hyperplane. In PR minus 1x0. So, and let's fix that, and let's assume this is the divisor of S, and S is a coordinate. S is some fixed coordinate of a coordinate of this projective space. So let's fix a coordinate S and consider this hyperplane. Then let's consider the following. This is the divisor of E0. Let me first write. So this is in ER minus 1 xn times delta n, and the T0 blah 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 Tn is a coordinate of this simplex, and this delta is a structure map from PR minus 1 xn. We have this way. Yes. Wait, something is wrong. Yeah. crucial, yes. 0 to, we have n structure map from P PR minus 1xn to PR minus 1x0. So this is a structure map, and I take a fullback of this function, and I take some like this. Then this is in this satisfy phase condition. So this is in PR minus 1 n xn n of Bloch's higher Bloch's cycle complex. And actually, sorry, so the product and actually which represents represents the one in usual Chow group. So this is not difficult at all, and this just gives a concrete representative of this Xi first Chern class of O1, and this okay. This depends on S, our starting point. So let gamma I is the one obtained from Si. So here S0 to SR minus 1 is a coordinate of PR minus 1x0. So we have R different representative of this element. So
Sorry, may I ask you a silly question?
Yes, of course, yes.
Yeah, so is it right that till this moment, speaking about this construction, you did not use modulus?
Not yet.
Not yet.
Modulus, yeah, modulus doesn't appear, not yet, but in 2 seconds, it will appear. Any other question? Okay, so yes, and we can check this Xi I. No, maybe different. Yeah, no, it was okay. Xi I stars intersect properly in an open neighborhood star of our modulus D. Because because our starting vector boundary is trivial along D, we can show in some open neighborhood this is a stupid one and intersect properly trivial one. Yeah. So this means we can take naive intersection of these cycles, and this is in the star P, where it is Pi. Maybe I should write R ES XN N, and sorry, star. some open neighborhood. And this, which represents R's power of xi. Okay, and the main claim of this construction is this intersection, this one. So this was R minus 1. R minus 1 satisfies the modulus condition. Means that, so it means that this is in R, E, R minus 1, X, N star, and the modulus. X, N star times X, T. I think I don't have the time to explain why it satisfies the modulus condition, but we can just check by writing down everything. And also outside this our open neighborhood X star, we can use usual moving technique. Use usual moving to get intersection product of these things, and patching them together, we get xi r relative in pi naught of pi naught of r and p e times base change with modulus. So this is yeah, something is wrong. Okay, it's how can I write? Let me see. X I guess easier way to write about it here. Yes. And which lifts usual xi r without modulus. So this is usual cycle complex, so it satisfies Zariski descent. So this is just isomorphic to pi naught of EE, and it just usual tail group. Okay, so we get something. And now we use the moving lemma with modulus proved by Kai. So by Kai's moving, we have a well-defined map like this. Take limit of O or Nisnevich cover of X. Then we can define intersection product after taking this limit. So this goes to limit of X Nisnevich cover E XX tilde modulus P E. Yes, this one. Can you read? Yes, it should be okay. And we can define this map after taking this limit, and take the sum of this map. Then by the projective bundle formula, for the construction we use moving lemma, and once we constructed this kind of map, we can show this is equivalence by using the usual projective bundle formula. So from this, we conclude there exists Ci in this pi naught of this limit. This is exactly Nisnevich localization. So this is pi naught Nis XD such that which satisfies the formula like this. Zero in here. So this is construction. So we starting from the pair of a vector bundle with trivialization, we could construct some Chern class and in this relative cohomology cycle complex with modulus. And actually, we can extend this construction to higher Chern classes. So let me summarize the results as a theorem. So let X be actually I assume the smooth. I assume the X is smooth, but it's too much. And actually, we just need a scheme of finite type over a field, and the D is effective Cartier divisor such that the complement is smooth. In this setting, there exists Chern class. So this is a map from K star XD, or Kn XD to In of Nisnevich shiftification of cycle complex. Yes. Which such that this is functorial in XD, MSM, and coincide with Bloch's Chern class for when B is empty, and moreover, we can show this satisfy Whitney sum formula. So this is our main theorem. So by this Whitney sum formula, we can say associated Chern character is additive. So we have n x to this one pi n b star b. I forgot Misnevich-Floch simplification x. And this is the Chern character. So let's take tensor q is additive. So I mean group homomorphism. And by using this Chern character, we get some application. So this is, let's assume this is X is spec V. V is Henselian DVR over a field. And let me write the M to be the spec V divided by pi M. Then we get, after taking limit with respect to this thickening, the like this in the pi n. So yes, and take tensor product, and this is isomorphic to kn x dm, taking the limit q for us. Unfortunately, something here, kernel of pi m d star x dm to pi m g star x. So this is the usual higher Chern groups, and yeah, there is an external extra term like this, and okay, of course, after taking the tensor q. Yes, so we hope this is isomorphic to this K group, but at least we could, by using this Chern character, we could prove the Chern character is a split surjective, and the kernel is like this. Okay, so I think that's all what I wanted to talk, and the time is good, so let me finish here. Thank you.
Okay, let's all unmute and give Ryomei a round of applause. Everybody. Here. So maybe I can ask the first question. Do you have a more detailed description of the kernel in the last application?
No. I mean, we expect that this is 0, but we don't have any progress in this direction. Well, maybe in the future.
Okay, thanks. Any other questions?
Yes, Paul. I do have a question. This is Vanny Pan. Yes, suppose we are given with this about line bundles with modulus.
So you mean line bundle with trivialization, right?
Yeah. Suppose we have we are given with a smooth projective curve, and say several many even over algebraically closed fields, doesn't matter. And we pick up and we mark several many points.
Sorry, I couldn't catch.
And D, we marked several many points.
Okay.
2 points, I don't know, x1, x2. And we are given with a line bundle on x plus trivialization on this 2 points, x1, x2, which is our D. Is it? Yeah. So we can assign to this pair a kind of first Chern class.
Yes.
The Picard group. So how one can do this? We can take a section which coincides with trivialization. We can extend trivialization to a neighborhood, to an affine neighborhood of our 2 points. We will get a rational section of our line bundle, and then take usual, how is it called, usual divisor of this line bundle. So we will get a divisor which is support. We will get a divisor which is in the open complement x minus d.
Yes. Yes.
So this is a typical representative of the group of the relative Picard group of the group pic x comma z comma d. So
Yes.
so is it true that your construction in this very simple case for line bundles gives exactly this answer for relative Chern class, first Chern class of.
Yes,
Or at least, do you expect that it is the case?
I think so. And in the case of line bundles, it's much easier, and maybe the construction is the one you described. But previously, before our paper by Binta Saito, so it was proved a Picard group of XD is isomorphic to groups with modulus. Is it true?
Okay.
What's the condition?
Perhaps X is smooth and.
Oh yeah, Nisnevich. Oh yes, okay.
Maybe D should have I don't know an affine neighborhood. Maybe not.
Oh yeah, but maybe Federico said after Nisnevich this is true.
Okay.
Right?
Yes, yes. You have to take some purification, otherwise you might not have enough cycles, right? I mean, because yeah.
Okay, after Nisnevich specification might be okay, and yeah. So in the case of line bundle, we have a complete answer. Yeah.
Okay. Okay. Thank you.
Okay, good. Any other questions? Doesn't seem to be the case. So then thanks a lot, Ryomei, for your wonderful talk.
Thank you very much.